Hello everyone. In this video, we'll be going through LLaMA 2 paper, which is from Meta on a very high level. So LLaMA 2 has released in roughly June or July 2023. So now if you see, we are in 2024 and August or September as starting, and they have also released LLaMA 3 a couple of months back, which is multi-modal in nature. First, we will discuss the LLaMA 2 paper, and then we will see what are the things we can learn from the LLaMA 2, and then we can jump on to LLaMA 3 down the line. So before this, hope you have already watched the key takeaways we can learn from the LLaMA 1, which I have done quite some time back. If not, please give it a try, and let's get started on the LLaMA 2. So LLaMA 2 comes up with 4 variants. One is having a 7B, 7 billion and 13 billion, 34 and 70 billion. So at the time of the paper, they explicitly mentioned that all of them have open source except the model which is having 34 billion, which is not yet open sourced, but it can change in the future as well. But as of now, 34 billion, which is from the Meta LLaMA 2, that is not yet open sourced. So when it comes to the architecture or the way the LLaMA 2 has defined, it has some differences between LLaMA, the previous version, that is LLaMA 1. The differences is very minute, more or less they have kept the architecture the same. So one of the differences you can observe is the pre-training dataset. So in the LLaMA 2, they have roughly used 2 trillion tokens. If you see LLaMA 2, the paper mentioned 2 trillions, but in the LLaMA 3, they mentioned that 1.8 trillion was the tokens which was used for LLaMA 2. More or less, I think 1.8 and 2 trillions are both are almost similar. So you can consider as 2 trillions was the one, 2 trillions number of tokens, something was used to train LLaMA 2, and which is roughly a 40% more tokens compared to LLaMA 1. That is one of the major difference. And second difference is the context size, which is 2K in the LLaMA 1, and in the LLaMA 2 it is they have doubled it, increased to 4K. In fact, in LLaMA 3 it is 128K, which is I think 32x than the 4K. But anyway, we will discuss more when we discuss deeply into whenever we discuss LLaMA 3 down the line. And they have also implemented GQA, that is grouped query attention, but only for the bigger models. In case if you are not aware of what is GQA or MQA or MHA, I have made multiple videos on this. Please give it a try. In short, GQA is somewhat, it will get balanced between MHA and MQA. Multi-headed attention is really powerful, but it takes lot of computation. And group query attention is somewhat, makes it was somewhat in between the MHA multi-headed and as well as the multi-query attention, where it takes very less computation multi-query, but it doesn't perform well. So that's why GQA, I think they applied only for the bigger models, because it does make sense, because smaller models anyway you can able to scale it up even if you use MHA, right? And that's why they applied only for the 34 billion and the 70 billion model. And let's move ahead. And anyway, this is the diagram. They also even have it on their paper. That thing, but they have typical how a model has been trained. They put it on the beautiful image. They have done the pre-training and they have done the SFT tuning, and using RLHF they have tuned it, which is in a PPO and rejection sampling and other related things. We'll dig deeper into that down the line. So let's see some of the few of the training details. Of course, training comes into so much of components. One is the pre-training and second is the fine-tuning, which in fact LLaMA 2 follows iterative fine-tuning, and there is also SFT tuning and also reward model tuning. We will look into all of these components. So when it comes to the pre-training, as I mentioned, they have pre-trained with 2 trillion tokens, and they have applied RMS norm. What does it mean? That means if you remember how a decoder only model works, every sentences, what are the input, they will split into tokens, and token has to convert into embedding, right? And before injecting these embeddings to the attention layers or the next layers, there will be several kinds of normalization methods one can be applied. It could be batch normalization, or it could be RMS normalization, or whatever it is. So this kind of normalization helps you to get more stabilization while training the model. So when it comes to RMS normalization, given a vector x, you will try to vector, that means that it will have lot of elements. You will square each of the elements and you will take the mean all of those, and then you will take a root, and each of the elements will be divided by this number, and that's what RMS norm means. It is easier said than done. I think this is what the first layer, and they have applied this RMS norm in multiple layers in the LLaMA 2 model. So and when it comes to activation unit, SUGLU is the activation unit they have applied. So SUGLU, if you consider, it comes up with two functions. One is the switch functions, and second category is the GLU functions activation. Both are non-linear in nature. But whenever we discuss in some or the other way, let's discuss about what are these activations, and why there are so much of different types of activations, and how does each activations make sense. And coming back to the next, I think position embeddings. So there are like various ways of position embeddings. One is absolute and relative. In short, rope embedding is somewhat balances between these two. I try to go through the paper of rope, but I felt it is math heavy. That's why I think I'm not going to discuss much deeper in this video. But rope embedding is something, it has kind of become a norm. If you see every paper, they're more or less going to use a rope embedding, which I will be discussing in some other videos. But for now, I think you can go to SUGLU activation and rope and RMS norm. This is what is being used. And most of the architecture, as I mentioned couple of minutes back, it is from the LLaMA 1, and the batch size they have taken it as 4 million, and the tokenizer they kept same whatever they have used for BPE, and with a backup size of 32K. And if there are numbers, they're split into individual digits. That means if you have 123, that means we will have the 1, 2, 3 as separate layers, consider the separate tokens, not 123 combined together. And there are some hyperparameters. Even we will see some couple of hyperparameters even in the reward model, etc. But for now, we will just skip it and see what are the observation made so far. So as I was saying earlier, LLaMA 2 comes up with 4 variants: 7B to 70B, even 34, and somewhat in the middle as well. So one of the things which was observed was, as and when the model gets bigger, the learning rate decreases. And it makes sense too, because if you increase the learning rate as and when the model size increases, of course model tend to get overfitted, and it's a thin balance between these two. So bigger the model, lesser the learning rate. And after pre-training of 2 trillion tokens, they mentions that model still did not show any sign of saturation. I will show you a diagram at the end of this video why they are saying it. They were already giving a clue that LLaMA 3 was in its way. They mentions that so saturation is something where you'll see a plateau curve saying that this is what beyond this model might not be able to learn. But those signs they didn't see while training the LLaMA 2. We'll go through the what they have also made one graph. I think once I show you, that will be more clear. So let's go on to the more fine-tuning details. So supervised fine-tuning, so far whatever we have it as, they have just taken the internet data. Of course, they have applied hell a lot of safety measures to clean the training data set and then applied on it. And next comes the SFT. SFT training data is nothing but if you want to create an instruction data set, you ask questions and you create answers. And you combine these two together, and that's what your data looks like. It is not the case in the in 2 trillion tokens. It's just the flow of words or a flow of tokens, right? But here it is structured. That's why it is called supervised. One has to sit and design this method. I ask the question, this is how you should answer, and that itself will create a training data set. And if you look at the Anthropic, they also come up with a 3H as a methodology, right? When it comes to the meta, they majorly focus on two things. One is the helpfulness and safety. That means the answer given by the LLM, it has to be helpful, it has to be safety in nature too. So they majorly focus on these two things while creating the SFT training data set. Coming back to the next, quality is all you need. I think one of the takeaway you can take it from the LLaMA 2 paper is just this line, I just quoted as it is. So we know that even in the Hugging Face and there are so many other places where you can find the SFT data set. They mention that, of course, those are really millions of examples too. But the quality of the data set also matters. So what Meta has done is they have come up with 27,000 manually created SFT data set. They mentioned that the SFT model which is trained on this, it is performing much better than the millions of examples. In short, these are all having very high quality in nature, and all of the millions need not be in high quality in nature. So high quality examples from our own vendor, because Meta also tied up with so much of vendors to come up with this data, and that's what they mentioned that this is the data, vendor provided data has improved their results in at a large margin. In short, quality matters and not really the quantity. Let's move ahead, and again they talked about what are the hyperparameter used and other related stuff. SFT, they have 27k dataset. They have done it for 2 epochs and with a batch size of 64 and a sequence length of 4096. Okay, and while training it, they have combined together prompts and answer were concatenated with a special token in between. So this while doing a BAP propagation, they will be doing the BAP propagation only on the answer generated and not on the prompt or the X. Obviously it makes sense, right? Given X, the model has to predict Y, and the losses has computed only on the Y and not on the X. This is also what is something which is done. Now let's move ahead. Let's talk about what they have done it on the, yeah, this is what they have done it on the RLHF part. RLHF also has multiple components. We'll discuss those, but I think in short, let's discuss about the reward model. So I was talking about just a couple of minutes back, Meta has majorly concentrated on 2 things. One is the responses has to be helpful in nature and it has to be in safe, right? So let's see how they have handled these 2 things. So when it comes to the reward model, I think I have made a separate video on how RLHF and other things works. I think within a couple of weeks or a month, I think I will upload those 2. It will be clear. So there are various ways in which you can create a training data for reward model. Meta has followed a binary comparison where given a prompt where you'll get 2 answers. One is which answer would be the right one. That's what the binary comparison schemes. It has to choose between, it will give the 2 options. We need to give the 2 options, and the classifier is trained in such a way that it will choose one response and it will reject the other. Since we have 2 options, that's called binary comparison schema, and Meta has used this. There are like several other schemas as well where you can also create multiple answers, and on top of that you can do permutation combination, I think, which OpenAI did long back. But coming back to Meta, I think Meta has used binary comparison schema, and they also used, they also have separate what is that set of methods they have given, or the rules they have given for the annotators, how to annotate the data. And if you look at the paper, they have done like lot of test interview process to hire annotators. They have done like, they need to check their English, how they write it, the grammars, their understanding of the prompts, and how do you whether they will able to understand the guidelines they are given. They have done a lot of things before they're hiring the people. And those annotators, what they do is, they were asked to create a prompt, and they were forced to choose between 2 responses. So that means given a prompt, whatever the model has responded, they have to choose. There is no other option. That means either they have to select or they have to reject. But while selecting either select or reject, I think they also have the flexibility to choose one of these 5, whether the one which if they have selected, whether it is significantly better than the rejected, or that it is slightly better, or that it is like you are not sure, or that it is really worst. So they also get an option to choose these 2, and then Meta has made use of this in the future while training a reward model. And separate guidelines were chosen to the annotators, only for helpfulness and separately for safety. And the preferred safety response were categorized in 3 bins. Of course, when we have the safe and we have the unsafe, it's a 2:2. Given a response, it could be safe or unsafe. Both could be safe, both could be unsafe, and the response could be unsafe and the rejected could be safe. So they are, of course, they rejected the unsafe one, though it is correct, and also they might have dropped the responses which are unsafe in nature. Basically, they have taken the annotators data wherever it is helpfulness and safe too. And by doing this, they roughly created 1 million, I think it's just a little bit more than 1 million binary comparison data set were created, and they call it as meta reward modeling data. And in the future, whatever the testing and other related stuff being done, that was also a part of meta reward modeling data. So they mentioned that it could be challenging for a single reward model to understand both helpfulness and safety. That's why they have trained 2 separate reward models, and one for the safety and one for the helpfulness. For a single model, it may be challenging to take a trade-off between these 2, and that's the reason they have taken the help of 2 reward models. And both the reward models have initialized. There is reward model, what we expect from the reward model. Given a prompt, given the 2 answers, it has to come up with a very kind of a classifier saying that, hey, I will choose this response because this is helpful and safety in nature, and I'm going to reject this. This is what ideally we expect from the reward models. And you can think of it as a classifier, and you could have also used BERT classifier, or you can also use any kind of lightweight models as well. But typically while training the LLMs, this is what being used. So far what I have seen, they have done 2 trillion pre-training, and also 27,000 we have the SFT, they have done it, and that's what they call it as a checkpoint. There are also multiple versions of SFTs, but the recent checkpoint, that's what the reward models has initialized to. There is also very good and logical reason. It makes a lot of sense as well when they mention that they do this because whatever the reward model knows has to be exactly same as whatever the chart model knows. In case if it doesn't, there could be a chances of hallucination. So just to make sure that there is no hallucination and other related challenges, both of the reward models have been initialized to the pre-training chart models. But if you look into that, the pre-trained chart model or the SFTs, those are auto-regressive in nature. That is only decoder in nature. And if you see it, the job of it is to create a next token. But when it comes to encoder only models like BERT and Robota, these kind of series, it don't have the mechanism to create a next token. There is something called classifier head. So in this case, what they have done is they have used the decoder model. Of course, that is pre-trained chart model. That's what initialized to. But they have replaced the next token head with the classification head, using which you will get a reward score for the rejection or the selected outputs. In this way, they made use of decoder as a classifier, and using which they have built 2 reward models. And the newly collected data with the existing open source preference data sets, of course, whatever the data set, I think they also combined together with the open source. There are like so many data sets also, they combined together. They also briefed together about adding this did not make any negative effect, and they think that adding this might help. That's the reason they have added the open source data set too. And so usually when it comes to reward model, generally it tends to overfit, and people don't go beyond one epoch. In some fact, I read the papers that they don't sometimes not even go for one epoch too. But in this case, they have to go for a one epoch of a training data set and with a batch size of 1024, which is a very good number too. So the next component in the RLHF is iterative fine-tuning. So Meta used to get the data from the vendors or from the annotators on a weekly, and depending on that they used to train their RLHF. So they have like they go through iterative, they have like RLHF V1, V2 till they have RLHF V5. Let's see how they have gone through this. So there are two RLHF paradigm they have tried. One is PPO and second one is rejection sampling. We know PPO is something, OpenAI has worked on 2019 and they have applied this in various kinds of model including 3.5 and GPT-4 too. So when it comes to the rejection sampling, there are nothing but you have the prompt, you ask the model multiple times with varying temperature to get different kinds of output, and you pass all of these outputs for a reward model, and we know reward model gives a scores, and you take the output which is having a highest score, and the selected outputs will be used for the gradient update. So this is what nothing but the rejection sampling, and Meta also has used the rejection sampling while training their models. But they have not used rejection sampling alone for all of V1, V2 and V5 versions of RLHF, but we'll see how they have made use of PPO2 along with the rejection sampling to train the RLHF models. And they mentioned that there is a little bit different between the PPO and the rejection sample, but if you look into high level, the fundamentals of these two are like very close and might not make much of a difference. In PPO, what you'll do is, you'll take the one sample, one prompt, you will take one output from the recently iterated model. But whereas in the rejection sample, you will take number of outputs, maybe the K could be 50, 80 or 100 from the same model but with a different varying temperature, and then you apply the reward model to select one output which will be useful for the gradient update. But more or less it's gonna do the similar stuff. And this is also quoted in the paper too. The fundamental differences between the two RL algorithms are less pronounced. And as I mentioned, there are like 5 versions, right? V1 to V5. Until the RLHF V4, only rejection sampling fine-tuning was used. That means you have the prompt, you ask the model multiple times, you choose one, and then you use that for the iteration of the next V5. And after the two, but for the RLHF V5, they have combined PPO on top of the resulting rejection sampling. They applied the rejection sampling checkpoint and then they applied the PPO too. That's why I was saying, they mixed all of these to come up with the LLaMA 2 RLHF V5 in this use case. And our rejection sampling was done only on the 70 billion model and not on the 7B or any lightweight models. One of the reason is that because larger model has the bigger capabilities and lighter models might not have this much capabilities, and by doing this generation from the 70 billion we can use the data set to train the 7 billion models too. By doing this we can also kind of something similar to like distilling the models. It makes sense when you look into the on a higher level. It makes a lot of sense too. That means that just distilling the larger model capabilities, we are injecting the larger model capabilities into the smaller ones. And there is something which they mentioned on what happened while training the RLHF V3. So they may every time whenever they used to get the data from the people, they have trained RLHF V1, V2, V3. Every time they used to do the rejection sampling, they always, until V3, they used to take the previous version rejection sampling and then do the training. So they observed one of the things that means if you want to train RLHF V3, they used to do the rejection sampling only on the V2. So this lead to it seems like catastrophic forgetting. That's what they mentioned it. Not catastrophic. They mentioned that model might have forgotten, but all of things that the model has forgotten, the things which has already learnt in V1, V2, that is something on the future research. That's what they have mentioned. But to get rid of, what I have done is the rejection sampling not only done on the previous version, that is V2, but they also combined together RLHF V1 and V2, and they have taken samples from both, and then they've gone to the reward models, whichever the answer comes up with the high, and that's what used for the next. And that's what they have done for the RLHF V3, A4 and so on. Then that's what they mentioned in the top performing samples, not only from the previous but combined together of RLHF V1 and V2. Coming back to the hyperparameters, they have like, of course we discussed, there are a lot of hyperparameters discussed about so far, even the pre-training, SFTs, reward modeling. Here as well they also used few of the parameters, but one of the things is they also use the KL divergence here. They have used FSDP because you know that one is a bigger model, these don't fit into one single box or one single node. That's why they have gone with the FSDP, which is a very research oriented tool. It is very difficult to make the things works too, and I'll see whether if I could able to make a video on the FSDP and how it works practically. Coming back to the one, there is also one of the things they talked a lot in the LLaMA 2 paper is ghost attention, but they have not talked about any of these in the LLaMA 3. Ghost attention, very fancy name, but let's see what it does. When it comes to conversations, let's see what are turns and other things. For example, if you see here, there is something called who are you, it gives some answers, and this is a user and this is assistance. User, assistance, user, assistance. We call this as a conversation. In fact, it is a multi-turn conversation. You ask a question, it will give the answer. You ask a question back, it will give the answer. So there are like 1, 2, 3 turns, and here as well there are like multiple turns. Usually in the initial, there could be an instruction saying that always answer with emojis, or always answer with emojis, or it could be something like always reply like how Shakespeare used to reply, maybe in part of a poem or whatever it is. So they observed that if they have not applied a mechanism called ghost attention, usually in the second or the third term the model used to forget the initial instructions. If you look at this example, the initial instruction is to know whatever the question I ask, you're gonna reply with the emojis. The first question which was asked, who are you, and it has rejected, it has answered with the emojis. But next question, if it asks like how to go from Paris to New York, it started answering without using emojis. So how do you remember even in the multiple turns the initial instructions? That's what ghost attention does. In short, what they does it, and this is what I could able to understand. That's what I have written in this book, and in fact this is a Notion site. I have published it. I will also attach this in the description section of the video. But when it come back to ghost attention, not much detailed information mentioned in the paper, but this is what I could able to understand. So if you want to make sure that model remembers the instruction, they have done these things, attaching these instructions for every of the user messages as a step 1, and using this they could able to create a training data set. That means who are you, and always answer with the emojis, and even for this they have prepared something like always answer with the emojis, so that it will answer it. So this is how they made use of it to create a training data set. But we know the same data set cannot be used at the inference time, because having this, first of all, it will increase the context size, and it is something not feasible at all. And what they have done it is at the last turn, when doing the back propagation, sometimes they will do the short form as well. Maybe if the instruction is something like behave as if like you are a Shakespeare, maybe the in the short form in the last instructions it will be something like behave like Shakespeare, not like too elaborated, or something like author is Shakespeare, or an actor like Shakespeare, or actor hyphen Shakespeare. They'll use some kind of short forms here, and the next step they will remove the, if you want to do the training after this. They will remove the added instructions for whatever the data had created, and they will do the propagation only on the generated, and the loss for the previous term they will set up to 0. And but I think this is what I could able to understand. But if you want to go deeper into that, I think please refer to the paper. But it seems that and after this they mentioned that it could able to even to support 20 turns as well. But earlier even the 2 to 3 turns it used to fail. But after applying this ghost attention, I think it has started going even 20 turns too. But if you want to know more details, please go through that. But this is what I could able to understand from what they mentioned about ghost attention. But there is no mention of ghost attention in LLaMA 3 at all. And here are some of the results. I think I will not go through the results very deeply. They have gone through the annotators, and they have gone through the GPT-4 as a judge, and they have done lot of things. And they mentioned that this is what they have also have like a set of 4,000 data points on which they used to do the testing and evaluation, both for the annotators as well as GPT-4 as a judge. And when it comes to the paper, there are two things which they majorly talked about, and two of the things repeatedly talked about, not too much talked about. One is on the safety measures, and they mentioned multiple times that this is the safety things they have done. If you look at it, that safety word itself has occurred so much of times in the paper. And second thing which I talked about too much is they mentioned that no meta user data has been used. These are the two major things they have given lot of emphasizes in the LLaMA 2 paper. Maybe because of the things happened with the US elections whenever it happened like a few years back. That could be the reason, but I'm not sure. But I think these are two major things, especially on the safety side. We'll go through what are the things they have done. They have done a lot of work. So they also mentioned that while in the pre-training dataset, they didn't go through the cleaning of the procedure, cleaning of the data thoroughly. That could be maybe for the future research too. But they also mentioned one of the point that it is by a choice and not by a chance. That means that if you want to detect something like a hate speech, then if you want to use the model to detect a hate speech, the model has to understand what is a hate speech. If the model doesn't understand the hate speech, then you will not be able to identify whether a speech is hate or not hate, right? And if you remove this kind of a hateful things, hate speech from the training data set, you are kind of removing the capability from the model to recognize a hate speech. And that's what they have mentioned it, and that is one of the reasons they didn't go through the cleaning procedure thoroughly. But they also gone through that, few of the things which is interesting is in the training data set, whenever the people is mentioned, they usually the data is talking about men, as well the woman. It is kind of created as a bias towards certain gender. Even whenever the he versus she, I think the number of mentions of he is very higher than the mention of she. That could be the reasons model might not able to understand the context wherever she is mentioned. They also talked about religion, where Christian is most number of times it is mentioned. They also used kind of a hatred, but in a sense they have classified, they have trained one more model to classify each sentence whether it is a hate or not, and they removed certain things. And they have done a lot of similar stuff while cleaning of the training data set. And even in the LLaMA 1, we have seen that language identification. Personally, I have used this model. This model is really gonna help you in case if you want to detect non-English documents. In fact, they have used this too. And they have also used lot of safety benchmarks and safety models, safety data set to make sure that their models are in place. It could be truthfulness, or it could be toxicity, whether how model is your toxic, and whether it is bias. I think we just discussed about the gender bias and religion bias and other related stuff. They have used multiple data sets to all of those things. But this is what one of the observation which I found out, LLaMA 2 of course comes up with various variants, and the 7 billion, which is the least variant, it was bit better in reducing the toxicity compared to the bigger models. Maybe one of the reason is bigger models might have seen the different kinds of data set than the LLaMA 2 7 billion. They also mentioned that LLaMA 2 does not outperform other models on the toxicity metrics for the just reason we just discussed. Hateful trials, you want that model to be performed, and adding this might helpful for the downstream task too. This I found this to be like one of the good information. We always tend to believe that remove this bad information data set, but from the other angle it could also be helpful, but not sure how it has been taken in the LLaMA 3 and the rest of the papers too. Again, safety, SFT training, and what they have measured it on the RLHF, they have supervised fine tuning, and whatever you named it as, everywhere I think safety has been taken care, and several models have been built to make sure that it is helpful as well as it is safety in nature. They also made a team of I think 300 to 350, they called as red team, and basically they asked this team to test the model to get the unsafe responses and report it to the team, so that it will help as a fallback loop and they can able to retrain it. And it has like, it could be ethical, it could be legal, it could be financial, it could be of any of the angles. I'll show you. I think these are the one. Yeah, they have cyber security, election fraud, right? So these are the various topics they have done the red teaming on top of it. And they have also has done a lot of things on the temporal perception. That means if you mention that cutoff date is 1940 and asking about what happened in the World War II, so basically they don't want LLaMA 2 to answer it. So kind of it helps in reducing the hallucination too. I know this is a quite long video comparatively, and before me wrapping up this video, I'll see whether I have missed any of those some of the nitty-gritty details. Oh yeah, this is what initially I was talking about the saturation point. If you look at this graph, basically this number of tokens 2 billion, and that's what is in the x-axis. And training PPL law, I think this is a loss. I think if you look into this, red is something which is in the 7 billion, and 70 billion is the one which is in pink. Of course, pink is having a lesser loss than 7B, and if you see it, that's what they mentioned, that they still did not show a sign of saturation. If it had shown a sign of saturation, they should have seen a plateau line here. That means it has the capacity to add more tokens. Maybe if you had a 3 trillions or 4 trillions, the model might have gone through this, and after certain duration it might have plateaued. If you say that could be one of the reason why LLaMA 3 might have gone to 15 trillions in 15.6 or somewhere around that trillions. So I think one of the things is carbon footprint. They mentioned that cumulatively they have used 3.3 million GPU hours. That means that for 7B, this is the SIP GPU hours, and 13B, this is the GPU hours, and etc. But I think 3.3 million could be the minimal. But being a data scientist, I can say that you need to do lot of experiment before training a bigger models. In fact, even if you want to, what are the things they have changed from architecture from LLaMA 1 to LLaMA 3, they have also gone through, I think I can search it. Architecture changes from compared to LLaMA 1. What they have done it is, they have taken 150 billion tokens, and they have taken a 30 billion model size, and they have trained this multiple times to whether should you go with MQA. If you go with MQA, what are the challenges, GQ and other related things. But they also spent GPU for this, right? They mentioned that they have 800. But what happened to carbon footprint for those one? So anyway, these are the things goes not mentioned, but 3.3 million I think I'd consider as a minimal things what they have spent on. Okay, all right. I think I'm almost end of this paper. Let me see if I wanted to add anything. That is this. Yeah, I think I have covered all of. But if you are interested, please go through this paper. It is really informative too. Hope you'll at least in this video, I think I have gone through majority of the highlights. So thank you so much for watching this video.